Free energy. Sounds like an advertisement for something, doesn't it? What we mean by free energy is in a chemical reaction or a physical process, any energy that is not being used within the process that's available to do work is called free energy. Okay? Oftentimes it's called Gibbs free energy after J. Willard Gibbs, who was the first to talk about it in terms of chemical processes. Okay? So it's represented by the letter G. Again, it's a state function, and it helps you to figure out the temperature dependence of spontaneity. In other words, whether temperature is an important factor or not. Okay, the definition of G, okay, the definition of Gibbs free energy is that it is equal to the enthalpy H minus the product of temperature and entropy. Okay. We can't measure state functions directly. We can only measure them from before and after, which means delta state functions. So delta G, therefore, would be equal to delta H minus T delta S. T is constant. When we're going to use this, it's got to be constant. So, and since it's constant, it's not changing, we don't need a delta sign in front of it. Okay? So that right there is a very important formula in understanding temperature's effect on spontaneity and on spontaneity in general. If I take my delta G equals delta H minus T delta S, and I divide each by negative T, okay, you may recognize delta H over negative T, or negative delta H over T. Well, that's our expression for the heat of the entropy of surroundings, isn't it? And T over negative T will cancel, and it'll change that negative sign between those two terms to a positive sign. And delta S, remember, when there's no subscript, refers to the system. So really, I can rewrite this as negative delta G over T is equal to delta S of the surroundings plus delta S of the system. Well, wait, delta S of the surroundings plus delta S of the system, that's equal to the entropy of the universe, isn't it? Okay, so as long as we keep pressure constant and temperature constant, delta S of the universe is equal to negative delta G over T. Okay, so if delta S of the universe is positive, in other words, the universe is becoming more chaotic, what sign would delta G have to have according to this relationship? In order for delta S to be positive, delta G has to be negative, right? So why can't delta G be positive? Well, if delta G is positive, then that would give you a negative value for delta S of the universe. And that would be going towards more order. And the universe tends towards greater disorder. Okay? So for a spontaneous situation, delta G has to be negative. Very similar to the sign convention for delta H. Okay? So H2O solid to H2O liquid, melting ice. Right? Delta H is 6.03 times 10 to the third joules per mole. That is the heat of fusion of water. Heat of fusion, the amount of heat necessary to melt 1 mole of water. All right, we know that from a previous chapter. Delta S for this process is 22.1 joules per mole Kelvin. So we're working in moles here. The little degree sign by the delta H, that indicates that this is per mole and at 25 degrees Celsius. Okay, so the reaction's values are in opposition. Delta H, endothermic, tells me that this should not be spontaneous because you have to put energy into it. Remember, spontaneous means you don't do anything, right? This tells me that it shouldn't be spontaneous because I have to put energy in. But delta S is also positive, which means that as water melts, as ice melts, it becomes less ordered, and that should be spontaneous, right? It should be something that happens automatically because the universe wants to become more spontaneous. So what do? That means the temperature determines the spontaneity, okay? So at negative 10 degrees, is this a spontaneous process? Well, qualitatively, we know that ice won't melt spontaneously at negative 10 degrees. It isn't, but can we prove it? Okay, well, delta H is endothermic, right? Delta S is increasing, so let's prove it. Delta G is equal to delta H minus T times delta S. Make sure your units match. We get delta G of 2.2 times 10 to the second joules per mole. Okay? So if delta G is not negative, then the process is not spontaneous. So the reverse process is spontaneous at minus 10. In other words, will water freeze spontaneously at minus 10? Absolutely. Yeah, reverse process. Okay. What could be another way to check for that? Check to see if delta S of the universe is positive. How do we solve for delta S of surroundings? Okay, use delta H and delta T. So at minus 10 degrees, this is spontaneous. Here's the other way to do it. Delta S of surroundings, delta H over T, negative delta H over T. Delta S of surroundings is negative 22.9 joules per mole Kelvin. Delta S of the universe is delta S of system plus delta S of surroundings. So I add those two together, I get negative 0.8. Delta S of the universe has a negative sign. It's not a spontaneous process. Okay? How about at 0 degrees? Well, qualitatively, what do we know? Water melts at 0 degrees, so that should be at equilibrium, right? So that means that delta S of the universe should be 0. Well, let's see what happens. Delta G is equal to delta H minus T delta S. Plug in our values. The only thing that's changed here is the T to 273. We get delta G is equal to 0. Hey, that's clever. Delta S surroundings, using the other way, negative delta H over T. We get delta S surroundings is negative 22.1. When we solve for delta S of the universe, we add those two together, we get 0. So it's at equilibrium. Okay? So no shift. What about at positive 10 degrees? Okay, does ice melt spontaneously at 10 degrees? Yes, it should. Not very quickly, but we don't care about kinetics here. We care about is it spontaneous, right? So let's plug it in and see. If you do the calculation, you'll see that delta S of the universe is positive, delta G is negative, both indicators of spontaneity. So those are the two ways to tell if a process is going to be spontaneous. If delta G has a negative sign, it has to be spontaneous. If delta S of the universe, not the system or the surroundings, the universe has a positive sign, it has to be spontaneous. Two ways, the only two ways to determine spontaneity is to look at those two things, either or, depending on what you're given. Okay? So this is a summary of what we just did, taken from your book. When delta S of the universe is 0, will delta G always be 0? Think about it. See if you can figure it out. How about this one? How do the signs of delta S of the universe and delta G relate? Think about it. You should be able to answer those two questions now. Okay? Now, how about enthalpy's relationship to entropy? Okay, H and S, enthalpy and entropy, when they're in opposition, in other words, when the reaction is endothermic and it's becoming more ordered, or the reaction is exothermic and the system is becoming less ordered, they're in opposition for spontaneity, okay? Then it depends on the temperature. So in opposition means that the two values are telling you opposite things about spontaneity. So delta S positive value tells you, yes, spontaneous, becoming less ordered. Delta H positive value says, no, you have to put energy in, that's not spontaneous. Okay? Or negative delta S, it's becoming more ordered, not spontaneous, but it's giving off energy, spontaneous. Those are in opposition. Okay? The exothermic direction of the process, whatever is exothermic, is going to be spontaneous at low temperatures. Okay? And vice versa. So this is another summary from your text that will tell you a little bit about spontaneity and how we deal with it in terms of delta H and delta S. And it's a good idea to look through these tables and make sure that you kind of understand what's going on there. It helps you predict. Okay, so here we've got liquid bromine to gas bromine, and we want to know at what temperature is this reaction spontaneous at 1 atmosphere of pressure. Delta H for this reaction is 31.0 kilojoules per mole. Delta S is 93.0 joules per mole Kelvin. It's endothermic. That should be non-spontaneous, but it's also got a positive delta S. It should be spontaneous, so they're in opposition. The reaction will just become spontaneous when bromine liquid starts to turn into bromine gas, in other words, at the boiling point. So that's what we're looking for, is the temperature at which this will boil. Boiling happens at equilibrium. At equilibrium, delta G is equal to 0. Okay? Delta H is exothermic, delta S is increasing chaos. So delta G is going to be equal to 0 at this particular, under this situation. So delta G is less than 0, but 0 is greater than, so that's another way of saying it's equal to 0 at this point. Okay? And we plug in our values. We've transformed delta H into joules, and we don't know what T is, so we're going to solve for T here. Okay? T comes out to be needing to be greater than 333 kelvins in order for this to happen spontaneously, but less than 333 kelvins it will not. Okay, the reverse will be spontaneous. And if you are exactly equal to 333 kelvins, you will be at equilibrium. Delta G will be equal to 0, and you'll be, that's the boiling point right there.